This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
So we'll have a short lecture investigating cosmology at later times. We studied cosmology at earlier times, at least we made an observation. We studied cosmology in general and we looked at a consequence at early times. And now we look at later times and we will now consider various types of matter at the same time. Now consider various matter types simultaneously, because as already someone of you asked, what happens if you have several matter types present at the same time? That's a realistic situation. You cannot say, oh, let's assume the universe is made of photons. Well, it isn't. There's lots of stuff in the universe and you have to consider that. But, pardon me? So let's recall, however, what we learned. We learned that if we have equations of state that are linear, and I will not go away from that because we're writing down simple models. Of course, if you're a cosmologist, you may have many, many reasons to generalize what we're doing here. And the purpose of these introductory lectures is to give you a taste and the basic ideas. And of course, with whatever assumption you're not happy, you go and generalize it. And of course, people did that. So for instance, I was asked in the break, what happens if you drop some of the Killing symmetries? Well, then you get non-isotropic universes, for instance, and then you get other models. So for instance, there are the Bianchi models of the universe. We looked at the so-called Friedmann-Robertson-Walker model. It's the homogeneous and isotropic cosmology. So many such generalizations, of course, are being looked at because cosmologists try to understand the data. Nevertheless, some amount of modeling is always involved because you need to make an abstraction from the local structure, which is extremely rich, and for them you cannot, including every detail, you simply cannot solve the Einstein equations. So some amount of modeling is always required, but of course you can be very clever and say, I do not make a model by just writing down something, I make a model by really trying to derive this from fundamental principles and so on. And of course, the better a cosmologist you will be. Anyway, so the purpose of these lectures is to give you the basic ideas, and the basic ideas, if we make our assumptions explicit, there is nothing dishonorable about making such assumptions. It is an assumption nevertheless. You know the game. So our equations of state, I will always assume that this is this one for omega equals constant, and from that we will now not deviate. So for each matter type, and then for each matter type you may have a different omega I equals 1 to number of matter types that you do have. Okay, fine. So obviously then you have different pressures and different densities for precisely those matter types. Okay, these different equations of state. Now, however, what we have learned, we learned that independent of the matter type, it's true that h squared scales like the density, scales like a to the minus n of omega. And what was the omega? Let's make again our little table, and maybe this time I would ask the blackboard erasers to maybe not delete this table for a while. Here? Okay. So you see the erasing procedure is not homogeneous. It needs to be right up there. Okay, good. So there's the omega. And obviously we had, not obviously, we had radiation. So let me write here what the matter type was. The type was radiation. Then we had omega 0 that we called dust. That was pressureless fluid. We had -1 was a cosmological constant. Well, let's leave it there, okay? We do radiation, dust, and cosmological constant. and or maybe I want later on the omega kappa too. Yeah, and we have the spatial curvature. But let's not consider spatial curvature as matter, because we're going to rewrite the Friedmann equation, especially the acceleration equation, in a way that will use the spatial curvature separately. Okay, so let's take these three types. You add your favorite other type, if it makes any sense. But there are these numbers n appearing, n of omega, and n of omega was 3 times. N of omega was 3 times 1 plus omega. So instead of remembering the omega, we could remember the n. Aha. N equals, omega equals 0, n equals 3. Omega equals minus 1, n equals 0. Omega equals a third, that's 3/3 plus 1/3 is 4/3, over 3 is 4. Okay, so let's have these guys here. I don't know what I wanted to put in the other column. It doesn't matter, it's a nice empty column, right? Okay, so please do not erase. Well, one could put in the time evolution, but yeah, why not? Okay, so let's say what's the A of t? How does the A evolve? And we found that for the cosmological constant it was special. It evolved exponentially like this for a constant h. And for the others it was this power law. A of t was t to the 2 by n. T to the 2 by n is here. Yeah, it's square, 1/2. Aha, yeah, of course. N is 4. 1/2. T to the 2 by n is 2/3. Exactly. So those were this is the scale factor, how it evolves for radiation, how it evolves for dust, how it evolves for cosmological constant. That is something we found out. We further found out that for all matter types not equal to cosmological constant, so that's an exception, the rho invariably went like t to the minus 2. That's stuff we observed, right? That's just from this homogeneous and isotropic universe. Okay. Now, let's make a definition. I already wrote it down. It's the Hubble function. So this is all you need to know, okay? And all that now comes is terminology, but it's terminology that's heavily used, and it makes the equation simpler, so why not use it? The Hubble function is simply the function h of t that is a dot by a. That's the Hubble function, okay? And the Hubble function has to do with the age of the universe. Why? Well, if the rho goes like the t to the minus 2, from this we learn, and that we will show in the tutorials, right? You can show that h goes like t inverse. And you know that at t equals 0, boom, Big Bang. Aha! So, and this guy can be measured because it has to do with the expansion of the universe. The Hubble function, which in this case is a Hubble constant, if you have only a cosmological constant, otherwise it's a function. And so it's related, roughly speaking, H inverse is the age of the universe. I mean, it's a rather remarkable number that you can measure the age of the universe. First of all, it has an age because it has a birthday, right? The Big Bang is the birthday of the universe. Let's hope we don't celebrate it ever. So, okay, it's quite remarkable that you can calculate this from this theory. Who would have thought that? Einstein didn't set out to calculate the age of the universe. It's a rather preposterous aim, but nevertheless, it drops out. Okay, so that's the Hubble constant. But then there are more interesting objects, and they're called density parameters. Well, there may be functions, but for linear evolution laws, for linear equations of state like those, they're actually constants. So let's call them parameters, but keep in mind that in this jargon, you should never ever deduce anything from what it is called. You only look at the definition. And so you have a density parameter. Density parameter for matter of density rho. Say, well, if you have the density, why do you need a density parameter? Well, you like to normalize this in a certain way. You call this omega. Now you may have several matter types, so I write a small I, and you know in here the I always runs from 1 to a number of matter types. Okay? So for each matter type that has a density rho I, which is everyone, you get a density parameter capital omega I, and this one first comes with a bunch of constants, 8 pi gn third. Why do we put them? Well, of course, they're not relevant. They're just there because we use that later in the equations. The equations become perfectly simple if these constants are absorbed in here. Okay, but that is, of course, meaningless. It's just a rescaling. And then the relevant thing is that you have the density in there linearly. So that's why it's called a density parameter, because it scales linearly with the density, but it's normalized with the Hubble constant squared, or the Hubble function squared. So unless you're in a purely cosmological constant scenario and no other matter present, this is really scaling by a constant. But if you have other matter types, you know the Hubble constant isn't quite that constant. It's a function, right? It goes like t to the minus 1. And then we like the scaling because this is a nicer quantity if we plug it into the equations. We're going to rewrite the equations using these guys. So this is for the matter types. Actually, matter of density, but it doesn't work for the fake matter that makes spatial curvature, or if you have a spatial curvature, I said you can consider this as fake matter, or if you have a cosmological constant, it's like fake matter with such a equation of state where the omega is -1, right? I mean, actually, only matter is only this stuff here and different models, and the cosmological constant didn't come by putting it in an energy momentum tensor. It came from the other side of the Einstein equation. But you could think of it as a contribution to the energy momentum tensor, and then it would correspond to a fluid of omega is -1. You look critical, Julian.
Strange concept.
What's strange? It takes taking a term from one side of the equation to the other side. Second grade. It's not strange. No, it's not strange. The cosmological constant comes in the Einstein equations at the level of the action as an addition here, and square root minus g. Plus you add a matter Lagrangian, not Lagrangian density because you already took care of that. It's the associativity of addition that allows you to do this. And yeah, that's it. Okay? Good. So it's not strange to do that. It's maybe surprising that it works. But from there, it's clear it does. Okay, so therefore, one also associates density parameters, but according to a different formula with the cosmological constant and with the fake curvature, with the spatial curvature, which now really doesn't come as matter into the game, right? I mean, so for the cosmological constant, you say, okay, it comes into the game as matter, but that the spatial curvature of your underlying 3 space, for which you have 3 choices, that can be understood as a matter contribution. I mean, that's really just looking at the terms and saying it looks like matter for a certain omega. Okay? You can do this, but now once you've defined these density parameters, you have to make extra definitions for the density parameters. They're also called density parameters. I call them fake density parameters because they just absorb something under the same heading, which has actually a very different origin. Question?
I'm wondering, since we are calling it like the fake matter, so what's the physical meaning
Okay.
of the...
Okay, yes. So the cosmological constant I could just call matter. So for the cosmological constant, because I add it here, whether I say I add it here, that has historical reasons, rather than adding it to the matter Lagrangian. But of course, it could equally well be part of the matter Lagrangian. That's the associativity of addition here. So it's an artificial distinction to say it is not in the matter, it's in the geometry. What do you mean? You have an action, there's a sum. Who are you to tell me, right? This belongs to this rather than this. No, of course not. Well, and that's exactly your point, right? They say, what do you mean by fake matter? So for the cosmological constant, it's as good matter as all the rest. It's a bit of a funny matter because it's everywhere of negative pressure. But on the other hand, if you have a rubber band, it's also of negative pressure. Now you have a rubber band and you stretch it and it has negative pressure because it pulls you in. The energy momentum tensor for the cosmological constant is the cosmological constant times the metric. Because you vary with respect to the metric, and maybe some dressing factor here, roughly speaking. Okay? 1 second, I say one more thing. Now, so you could say, well, here the cosmological constant, I call it fake matter because the term looks different, but that's still, you could still consider it matter that has the same right. But now, however, if you start talking about the curvature, the spatial curvature kappa, which we have 3 choices, 0, +1, or -1, if we absorb the scale into the scale factor. I mean, that is strange because it doesn't appear anywhere in the Lagrangian. Well, of course, if you plug in a special solution into the field equation, it appears, but it comes from a totally different point. It comes from a symmetry assumption, gives a restriction. You have 3 types of ansatz you can make. Now, you say the ansatz I make is a matter type. That's a little strange, right? So, but formally, you can do that. And then you can forget about the difference between one and the other and treat them all the same and measure all the same and say this contribution I associate to this and so on. So that certainly deserves the name fake density parameter. But I said that's my personal terminology. I mean, you might equally drop that. Yes?
I mean, wouldn't then in a certain picture the cosmological constant introduce something like a gravitational force again? Because, I mean, in the Newtonian picture, where gravitation had something like a meaning of a force and would put things together. But, I mean, we got rid of it because now it's curvature of space. But if you introduce something which now pulls something together, this is like introducing again something like a force in this new type.
No, because the cosmological constant. I mean, that's the intuition. Understand the negative pressure, but the cosmological constant appears in here. I associate to the energy momentum tensor. It contributes to the matter contents of the universe, and that curves space-time even more or differently. Okay, so you add it, and the role it plays here is that it curves space-time more. Therefore, all the particle trajectories are modified as opposed to you don't have a cosmological constant. In that sense, it has an effect. It should have an effect, but it's not a force. It just contributes to the curvature via the Einstein equation. Okay, fine. So let me write down this. Okay.
In this omega equals -1, did we already put in the assumption that we assume lambda to be greater than 0?
No, because we will now write down the lambda explicitly in the density parameter. No, we didn't. Okay, so we have the first fake density parameter. That's for the spatial curvature kappa. So that deserves the name fake. For the spatial curvature kappa, so if it is present, we say we have a fake density present, which is omega kappa. So kappa is not included into the 1, 2 number of matter types. It's an extra type. Is minus kappa over h² a squared. We just have to define it that way so that we can treat this at the same level. And the third is then the pseudo-fake, so not quite such a fake. So let's put in brackets the pseudo-fake density parameter. But I agree, that's ridiculous. It could also be called the density parameter, but for the cosmological constant, you have to write it down in a different way. It's called omega down lambda, and it is lambda by 3h squared. Lambda by 3h squared. So the point is, ignore the terminology. Whether I call it density parameter, fake density parameter, I call it the flower concept, it doesn't matter. You have on the right-hand side of these definitions, you have quantities you know and you well understand, that are defined, that have a physical meaning. And on the left-hand side, you obviously have a combination of such quantities, and it's nicer to work with these combinations for the following reason. Using the Hubble function and the density parameters, we get, well, first of all, we get for the Friedmann equation, we can rewrite it. And look how nice it looks. I take the sum of all matter types from 1 to the number capital I of the matter types. So the number of matter types is capital I. And I add up all the density parameters for matter type 1, matter type 2, matter type 3. But I didn't want to call the kappas matter types, but I call, so you could say overall non-fake matter. So let's really say not fake here. Let's only say fake density parameter here. So you could also say it's the sum over all non-fake matter. So that includes the cosmological constant, meaning from 1 to I. But the fake matter you also add. Okay? You'll see in a second why I do it like this. Anyway, the sum of all of this is 1. That's the Friedmann equation. You can check. So that is more memorable, I guess, than the original Friedmann equation. Okay, so this is why one likes this. But then we have another equation. We had the equation which requires an acceleration equation. What was that? That was this A double dot, and that becomes H inverse squared A double dot over A. You could also set out to rewrite the A double dot over A using the H, but let's leave it this way, equals minus 1/2 sum over all non-fake matter, so including cosmological constant but not including the curvature, of 1 plus 3 omega I. So the omega from the linear equation of state makes a reappearance times the omega I. So you see that using the density parameters, both equations take a rather simpler form, and that is why cosmologists like to think of the matter types, including the cosmological constant, as matter types, and even in this equation, they like to also think of the spatial curvature, which you may choose to be 0, which means that this omega kappa goes out, or you may choose it to be plus 1 or minus 1, okay? They like to think of it as the same level, so you say sum all matter, fake or non-fake, it's 1, the density parameters, but down here it's only the non-fake matter, okay? So you have this and you say, okay, you redefined these quantities, what's the point? It looks nice, but what's the point? Well, you can immediately look at what I call, well, maybe that's what should have been called density parameter and Hubble function. Okay, so that was section 1 here. Density parameter and Hubble function. It's just these redefinitions and the Friedmann equations in those terms. And then the next step is the second dominant matter at various epochs, so stages of the evolution of the universe. So now you could think that you have to postulate which matter is dominant in the early universe from your physics intuition, and which matter is more important later on in the universe from your physics intuition. In fact, you don't need the intuition, you can calculate. We know that rho goes like a to the minus n of omega, right? So we know the density of the ith matter type goes like a to the minus n of the omega of the nth matter type. Omega is a constant. Now we also know, that's the first thing you know, the second thing we know is the not erased table here, but maybe the rest could slowly be erased, maybe the left blackboard. We know that the various matter types, radiation, dust, and cosmological constant, they have different n's. So let's write down the n's. What is the n for radiation? I write n gamma, like a gamma quantum, right? N gamma is 4, right? That's what we had, is 4 for radiation. Then we could have the n, the next lower one is 3, that's the one for dust. And here I write an m like matter, but what I really mean is dust. That's the terminology in cosmology, matter, and here we mean radiation. Okay, that is 3 from the table. Then you also can get from the table that the n for the kappa, if you include it in the table, would be a2. And the n for the lambda is actually a 0 for the cosmological constant. So this is the n you would formally associate with the spatial curvature. And that's the n you would associate formally with the cosmological constant. Okay? And this is true for any matter type, including cosmological constant. Remember, I emphasized some of the equations I wrote down are only valid for non-cosmological constant matter, but this one in particular is true for all matter. See the tutorials today where you will derive this. A very short derivation. It's good to do this yourself.
Do we assume kappa is negative?
No, we didn't assume R. No, this should be for any kappa.
For any kappa is
Yes.
okay.
That's the n. It's the density parameter for the kappa carries the kappa and carries the sign. Ah, you're right. I think I wrote in this table in the last lecture, I wrote something like this. No, sorry, that's minus 1/3. I'm sorry. No, the sign goes in the omega. Yeah, I was confused there. Now I see, now that you ask. That's just minus 1/3, and the sign comes from the omega in a second. Okay, so now you have that, and from that you can immediately conclude that the following is true. You can conclude that the density associated with the cosmological constant, which we just defined, scales like a squared, the density associated with spatial curvature, which in turn is proportional to, that is what I mean, proportional to, with a constant factor, proportional to a squared omega kappa, which in turn is proportional to a to the 3rd omega matter, so that's the dust, which in turn is proportional to a to the 4th omega for radiation. This follows immediately if you check the definitions of these density parameters, and what we wrote up here if you plug in these n's here and check how the density parameter has the rho in there. It's very obvious. Okay? So think about this. It's very easy. Okay? Aha. Now this is simply an observation, but it's an observation that tells you a lot. Why does this tell you a lot? Well, observation in an expanding universe, that means a universe where the Hubble function is at all times greater than 0 because it's a dot over a. That means the a increases all the time. That's an expanding universe. In an expanding universe, the later the time, the bigger the a, right? T1 less than T2 if and only if a of T1 less than a of T2. At later times, there's a bigger scale factor, right? Very simple. It's an expanding universe. But if that is true, then how do... Look at just this proportionality here for a second. You can look at any of these, but let's look at this one. There's an a to the third, there's an a to the fourth, so you can of course divide by a to the third. What remains is omega m scales like a times omega gamma. Right? So they're the same. So which is more important at late times? This one, which is higher? This one or the omega gamma? The matter, because the matter is 1,000 omega gamma or 1,000,000 or ever increasing. That means if you have, hence, we read off that if you have here time, which we now know starts at the Big Bang, great. This one, if you go forward in time, the ones to the left here become ever more important. And if you're at the beginning of time, where the scale factor is very small, this one is the most important one. That means in the early universe, the gamma dominates. The others may be there, but they're suppressed. So then slowly, the gamma is less important, and the matter starts to dominate. And then slowly, the matter is even less important. This is even further less important. And the spatial curvature you may have chosen or not to be there, or that may be there or not, dominates the evolution of the density. And at very late times, only the cosmological constant determines, is the dominant matter type in the universe that plays the biggest role. So I didn't have to speculate about the role of a cosmological constant in the early universe. There is none. It's highly suppressed. There would only be a role in the early universe if all the other matter types weren't there. Then, of course, it remains the dominant one because it's the only one. Okay? It's a political solution. If you eliminate all your competitors, right, then you stay dominant everywhere, right? But that's the only possibility. Otherwise, the other one starts to dominate. And that is a result of the theory. It's not a modeling assumption. That's good. That's good. So we have better control over the various epochs. So if a cosmologist says, well, lambda dominates at late times, that's a very mysterious statement unless you know this line of proportionality is implied by the Friedmann and acceleration equation. That's this. Okay, fine. So you have these dominant matter types at various times. Yes?
But didn't you say that the cosmological constant was added in order to make the universe expand, accelerate?
At late times.
At late times?
At late times.
Are we at late times now?
Yes.
Okay.
Do you know any later time than now? That's the terminology. We're at late time. We're at late time. Okay. I mean, you could say if we weren't at late time, maybe we couldn't have observed this yet, right? If there's other stuff present, because then this might be still dominating. And we have that stuff. And that's the standard model. That's our assumption, whether the spatial section is flat, spherical, or hyperbolic. And we'll see how this fares with observations. Yes?
So, but we speak only of if we have different types of matter which are dominating at which time, but we do not speak about converting one type into the other.
No.
Not included here.
Not here. No. No, that's not included. That's right. You may want to look at that, and people, in fact, people look at that, and there are conditions on nucleosynthesis and stuff like this, and you need a deceleration period, but not, as a second derivative is less than 0 and so on. So there are many, many results. They're all based on the model. That's right. I mean, obviously, one needs to look at this. This is a very simple-minded model that uses several types of matter. Yes?
We're a bit confused because this spatial curvature kappa we're talking about is obviously not caused by mass. So we just assume we're living in a sphere or a saddle or a flat space, and that's it. So
Yes,
we have
it's
no
there or it
reason for
isn't.
curvature.
It's there or it isn't, but if it's there, assume the spatial universe is S3, it's closed, has a finite volume, assume that's the case, then that doesn't play a big role in the early universe, and it doesn't play a dominant role in the late universe. But it plays a role somewhere in between.
So it's not an important assumption.
Well, not for late and not for early, but for in between it is. Okay, and whatever processes take place here, so you can say, when did, I don't know, the stars develop? When was structure formation? When was the cosmological microwave background being imprinted in the quantum fluctuation? Blah, 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 right? When took that place? And you try to figure out when happened what because of all the physics you know, which is more physics input, and then you slowly get a picture. And this is already very rough pictures of what could have been the most dominant matter type, density-wise, density parameter-wise, at which stage. It gives a first ordering principle to what you're looking at. And obviously cosmology is a fascinating and very big business today. Not only a business, it's a fascinating subject. It's extremely complicated because you need to take everything into account, from quantum field theory, plasmas, whatnot, the whole business. This is the zeroth order approximation to what's going on. Yes?
Is it already decided which value kappa took in order?
Yes, experiments say something, and I'll show in the diagram in a second.
So you stated we are at this late time where lambda dominates, and does this mean that, well, the matter is not dominating, so this, can this be interpreted as, okay, we take some galaxy cluster and according to its gravity it evolves and does stuff, but this has...
I don't know about any galaxy. As little as somebody dealing with a gas, who dealt with gases at the time? Who were these people? Who did the gas laws? What were they called? Tell me a name, help me. What? Boyle. Okay. Boyle didn't think about atoms. At this level, I'm not thinking about galaxies. I'm thinking about the fluid from very far away.
Yeah, so
Okay.
I think, but you say the matter in our universe has no impact, or nearly no impact on the evolution of the universe as a whole at our time now, because we are...
Less impact, yes.
Okay.
Not the dominant impact, yes. Yes, that's right. But I no longer have the resolution of, I don't even see a galaxy cluster, as little as in this room you see oxygen atoms.
Yeah, sure, but
Yes.
this whole dominance thing is about, okay, in the universe we have now, the matter evolves according to laws of gravity, but it has nearly no impact on the evolution of the universe as a whole, because that is dominant.
Yeah, I mean, I'm trying to draw, to make a metaphor for what actually is this exact line of proportionalities. I'm trying to bring them to life. But if you need to go back to this to answer any specific question. Yes?
So obviously the density of matter is being reduced a
in proportion to the density of the cosmological constant, for instance. It's proportionality. It doesn't tell you anything about the absolute value.
Okay, so maybe it's just this proportionality then, but I just wonder how we can have matter at all, like dominant matter at all as we have, if it's being reduced that much along the...
Well, we do have, yeah, but as I said, I mean, the point is you have a very thin, very non-dense, I mean, I'm in this room. You have a lot of air, okay? That's one fluid. And there's another fluid, that's all your noses, you know. We'll come back to this topic. So the point is, or all your bodies. And now the point is, what contributes more to gravity in this room, to the space-time curvature in this room? Your bodies or the oxygen molecules? Molecules? Well, you do, okay? So you have several types of matter, and here we're in a situation where you contribute more to that than, but you could have another situation, right, where you have, I don't know, with a very dense oxygen gas, filled with a very dense oxygen gas. You wouldn't be sitting quite so happily here, but it's the same audience. Then all of a sudden that could be so dense that it contributes more to gravity than you do. And in the evolution of the universe, these proportions, in a sense, these dominances, density-wise, they change according to this line. Yes?
If we now say it fades away, so the oxygen will fade away with time, and our bodies will fade away less with time.
No, well, it depends. I mean, it depends also on the statistical mechanics of this. How does it thin out? If you make space double as big, how does the density of a radiation change compared to the density of point bodies? You look at this in statistical mechanics, you get different results. The scale dependence, the volume dependence is not the same for different matter types. So this is in perfect accordance with, say, statistical considerations, because some are massive, they have a different phase space than those that are massless. Has to do with that. Yes?
Okay, I understand now the larger the universe grows, the less important the matter becomes. So that's somehow clear. But what's the interpretation of the cosmological constant then? Is it this dark matter you...
well, yeah, so some people say, I like to think of photons and little balls that don't interact and curvatures, but this guy I can't imagine, and it aids some people's imagination to invent names. And so you can call this dark energy. And then they say, well, it's a justified name because it's an energy, as you can see, well, an energy density, and you have dark because the cosmological constant is a matter type. I added to the energy momentum tensor, but none of the other matter has the lambda in it. Do you know the lambda? Where's the lambda in the Maxwell action? In Jackson. It isn't there. So the light doesn't couple to the lambda, roughly speaking. Okay? So the lambda stays there separately alone, not coupling to any of the other matter. Okay? So that means you couldn't detect it by other matter, because you can only detect something if it interacts. I can detect your head by throwing a ball if the ball is reflected, but for that the ball needs to interact with your head. Right? If it doesn't, I have a problem with detecting your head. Okay? Or with the light and so on. So if the lambda doesn't couple to anything else in your other matter actions, which is something we haven't seen, okay, then it's dark because you can shine any matter on it. It's not being reflected because it goes straight through it. Okay? So therefore it's dark energy. We don't see it other than through its gravitational effect, because it contributes to the energy momentum tensor. Hence the Einstein curvature sees it. But that's the only thing that sees it. Hence it's called dark energy. And then you can say, well, anyway, I'll show a diagram in a second. But that's just a name, dark energy. And then people could say, oh, you could have different types of dark energy. Well, what do you mean by dark energy? Well, you can call this dark energy. That's terminology. I try to avoid it. Yes?
If it is a constant in the Einstein equation, doesn't it mean that it is perfectly homogeneously distributed?
That's right. That's right. Yes. Yes, it is, like the ether. Okay, that's polemics. But the point is, it is. That's right. That's right.
Does a cosmological constant hurt the background independence?
as Giulini in his evening talk, in his unofficial evening talk, explained, one has to be very specific of what one means by background independence, because you can make any equations background independent in a sense.
But is not acted upon.
Well, any matter you put on somewhere is extra structure, if you wish. I think this question is not particularly meaningful. It depends on how I look at it. If I say, well, if you provide this density, omega, or the energy, then of course you have provided one, right? So how is it still background independent? It provides a background, but it depends on what you call a background. It's a rather, at this stage of technical definition, it's a rather ill-defined question, I think. Sounds good, but that's the case with many questions. Yes?
Yeah, but if I say that lambda is perfectly uniformly distributed in the universe, how then can I see a gravitational effect in smaller scale? Because
Well,
if I have the sun, I know, okay, there will be some effect, but if it's distributed...
no, you see it at a global scale. Now, if you only have a cosmological constant, the evolution is like e to the ht, right? And
So only at the global
it blows
scale,
up.
not by light deflection or things like that.
No, of course by light deflection, because if the universe changes in time, light is a time-like, a null geodesic, well, depending on what the whole overall circumstances are and so on, of course you see it also there. Yes?
But not in a spatial filiation.
Yep, but in a spatial foliation you see nothing, because the experiment needs to use massive or massless particles, and they always are transverse to spatial sections. Yes?
So in the model that we use, all the things are uniformly isotropic and everything, but of course in real life matter tends to agglomerate, and even radiation, you can have objects with more radiation. So
Yes.
would it be possible that also dark energy also agglomerates like this, or by the construction it cannot?
Of course, so some people say, okay, let me continue, because I first need to, I always want to give you answers that already depend on an experimental result I'm trying to show you in a second, right? So, okay, so let's, it's another urgent question. Okay, good. So, so let's look at a realistic late universe. Well, I shouldn't say realistic, I should say a more realistic late universe. I mean, these are all toy theories, and they can be slightly refined. So a realistic late universe, several matter types present. So let's assume we have matter, spatial curvature, and a cosmological constant. Yeah, let's say that. That is a three-dimensional parameter space that we have for these parameters, but the Friedmann equation says the sum of the three is 1. That means I could express, for instance, the omega kappa as 1 minus omega matter minus omega lambda. The Friedmann equation says if you have 3 density parameters, you only need to look at 2, because the third one is then determined by the Friedmann equation, right? Aha. So that is, hence, the parameter space for this model is omega m, comma, omega lambda, because the third one is automatically determined. You only need to track these 2. Now let's draw a picture of this. So here I have the omega lambda, and here I have the omega m, the density parameter for the dust, for the pressureless matter, which I imagine fills the universe. And here I have the density parameter for the cosmological constant, which I assume might be present. I don't know how much of this, and I don't know how much of that. And I also have present the omega kappa. But the omega kappa I don't need to look at, because if I know a point in this space, like this one, I know there's this density for that and that density for that. That could be an observation. Do you agree? I could look now and ask what's omega m and omega lambda. And that's in fact what the various experiments extract from their data on the basis of the model. Very importantly, not absolutely, but on the basis of the model, they extract that from their data. It's a very important caveat. Right? Okay, and then I know the omega kappa, because it will be 1 minus this minus that is the omega kappa. So now the cosmological constant, this guy here, is proportional to the cosmological constant if you go back to the definition. Let's look at this in the range from -1 bis 1, we'll see in a second why. And let's look at this in the range from 0 to 2. You'll see in a second why. Okay, so we have this model here. Now I can ask various questions in order to understand the space of possible measurements. Well, an observation would measure a point. I mean, a sufficiently precise observation. So classify the regions in this parameter space. Classify the regions in this parameter space. And obviously, if you say, hey, you forgot the omega gamma, what about the radiation in the universe? I say, yeah, okay, then draw a three-dimensional diagram. You have the omega gamma in there. Still, the omega kappa is then 1 minus omega m, omega lambda minus omega gamma. Right? Then you get a three-dimensional graph, and you have to put a point into a three-dimensional graph. Okay? But if we are interested in the late universe, the omega gamma is no more interesting. You remember? So we leave it out in the model. Why would we bother? Let's do a two-dimensional graph. Okay? Good. Right, so classify the regions in this parameter space. And the first thing you could ask is consider regions of spatial curvature kappa either greater 0, but I would also like to know the region where it's less than 0, and I would like to know the region where it's equal to 0. Aha! How did this go? Well, k equals 0, kappa equals 0 corresponds, please check the definition of omega kappa, corresponds to omega kappa being 0, right? Because it was proportional to kappa, the omega kappa. If one is 0, the other one is 0. Aha, but omega kappa is 1 minus omega m minus omega lambda. Agree? Why? It's the Friedmann equation. Hence, I have omega lambda equals, this is 0, equals omega m minus 1. Which line is that? Omega lambda is omega m minus 1. It's wrong at that, right? It's 1 minus omega m. Omega lambda goes to the other side, it's 1 minus omega m. What line is that? That's this one here. Right? So this straight line here, in a suitably curved blackboard plane, this is a straight line. This straight line here are all the observational data points I could have, which would yield kappa equals 0. You see, it's just a line. Anything to this side of it, you can check, has kappa greater than 0. You check by the same argument, but instead of the equal sign, you take the other sign. And everything to this side of it has kappa less than 0. You need to look very closely to see whether it's 0 or not. But anyway, that's what you can have. These are the two sides here. Then you can have I can ask another question. You could ask the acceleration of the expansion. What is that? Well, that's h to the minus 2 a double dot over a. Well, this one is always positive. This one is always positive. So if you are just interested in the sign, it doesn't matter what the factors in front are. You can again ask, where is it less than 0? Where is it greater than 0? And where's the acceleration of the universe 0? Where does the expansion accelerate? Where does it not? And where does it decelerate? That's interesting to look at. Now we look at the acceleration equation. So this was Friedmann. This here was the Friedmann equation. And now we have another equal sign. Now we use the acceleration equation. And what was that? It was something like minus 1/2 the sum over all non-fake matter types, I equals 1 to capital I, 1 plus 3 omega I, right? Yeah, 1 plus 3 omega I, omega I. Aha, so I only take the non-fake types, equals minus 1/2. Now the first type I want to look at is, the only non-fake types are m and lambda, they're matter types, right? M was dust. Which omega does dust have? 0. P equals 0 rho, because it is pressureless, has 0. So the first one is 1 plus 0 times omega matter, plus, so that means a minus 1/2. Next type is the lambda. What omega did the lambda have? Minus 1. 1 minus 3 is minus 2. Minus 2 times minus 1/2 is plus 1. Plus 1 times omega lambda. You agree? I think you do agree. So you have minus 1/2 omega m plus 1 omega lambda. So again, starting from this equal sign, if you want to get the line here, from here it follows omega lambda is plus 1/2 omega m. Aha. So if before we drew this yellow line, that was the line for kappa equals 0, and now we draw a blue line, that's the one for acceleration equal to 0, and its omega lambda is 1/2 m. It starts here, goes to the middle, goes to up here. That's this one. So this has, on this line, the acceleration of the expansion of the universe. Or the acceleration of the scale factor is 0. And you can again do the same calculation and check the signs. If you go in this direction, the acceleration is greater than 0. And if you go in this direction, the acceleration of the universe is less than 0. You can ask further questions. You can ask, in what region, what about recollapse? I think this question was asked before, right? Recollapse versus eternal acceleration. I mean, it seems very reasonable. So you say, oh, the universe expands, but there's matter in it. I mean, matter and energy. And, okay, some energy has this funny negative pressure type thing, the cosmological constant, but shouldn't the energy in there, the matter, try to lump together again? It flies apart, but shouldn't finally it fall together again? And that would then, okay, so I mean, that's a question that you can ask. So that you can say there is recollapse if and only if there exists a time t star in r plus 0. Please keep it. I need. Does there exist a time t star in r 0, such that the expansion of the universe actually comes to a standstill, and actually also that this is not only this, but this is a maximum. No, that the A is a maximum, that the second derivative also vanishes, and so on. So anyway, you know what I mean. You look at the scale factor, right? This is time, this is the A. Is there something like this? So there needs to be a turning point. And of course, you can write this in terms of an equation, right? You can ask when is the second derivative of the expansion 0, and if it's supposed to be a maximum, so that really goes back. I mean, you could come to a standstill and then go on. Then you know that you need the first derivative to be less than 0. No, something is strange here. The first derivative is 0, and the second derivative is less than 0 for a maximum, right? Okay, thank you. Okay, so as I said, undergraduate calculus. All replaced by differential geometry. No kidding. So the point is, you find the condition for this turning point, and you can write it down. And you look what the equations say. That can be written down. It's a little bit more complicated. What you find is the following. So you find the condition that the collapse just doesn't happen. So the division line between recollapse happens and eternal acceleration happens is the following. The division line runs along here, really exactly along here, and then it takes off a little here. And that's a complicated function which, however, can be analytically calculated. Some arc cosines in it and so on. And everything above here is eternal acceleration, eternal expansion, and everything down here is recollapse. It only depends in this model on the omega m and the omega lambda. And now you can investigate, well, are omega m and omega lambda actually constants? Well, it depends on your model. In our model they are, because in our model, recall that the rho went like t to the minus 2, and the h went like t inverse, and you have in the densities, the omegas are rho by h squared, quite obviously. Okay, anyway, so we're here, and now the question is, what does experiment say? This is all theory. These are possible universes we might have filled with this toy matter. What does the observations say? And the observations from various sources, and cosmologists believe from independent sources, not independent groups, but in a sense, one is supernova galaxy surveys and redshifts and whatnot, indicate that omega lambda is 0.7 and omega m is 0.3. Hang on a second. Yes, and omega kappa is 0 because it lies exactly on this line. And of course, it's an experiment, right? So the experiment rather says something like this, and says our universe is somewhere like there. So you might say, well, to a very big degree, kappa equals 0, a flat universe, that means spatially infinitely extended, is supported. But I mean, it's very easy to jump here or to jump here, right? Okay. And 70% of the energy density, energy density of the universe, 70% needs to be put in the cosmological constant, and only 30% comes from matter. But it's even worse. So, observations say 100%, that's the 1 in the Friedmann equation, equals 0% from the spatial curvature, yeah, spatial curvature contribution. And of course, there may be a little spatial curvature, plus 70% is the cosmological constant contribution. This is in order to explain the totality of observations, or a certain subtotality of observations, plus now there's 30% left, but the 30% are split in 25 plus 5, which we divide for other reasons, and only these 5% come from what we believe is standard model matter. Standard model of particle physics matter. So if we don't look into the universe and we go to accelerators and we shoot bananas onto oranges and we see what happens, and we study all the products of these collisions, we get all the particles of the standard model. That's what we get. This is quantum field theories, the three gauge theories, and or the electroweak and the strong interaction and all the zoo of particles that come with it. But that, what we believed in quantum field theory, in elementary particle physics, to be all the matter there is, at high energies as high as we can produce them in the lab. What we believed is all the matter there is only accounts for 5% of the matter and energy in the universe that you need in order to explain the observations in cosmology.
What about theories that...
Oh, one second. Don't steal the moment. So now the remaining stuff is not of this type, and it has certain properties, and people call it dark matter because, like the cosmological constant we introduced, which is just one model for dark energy, so dark matter, and I can call this dark energy. It's just terminology, right? It doesn't interact with any of that matter, but all our instruments are made from that matter, can only interact with that matter. So it could be that dark matter interacts with dark matter. I mean, it very likely does, and so on. But the point is, we don't have instruments built of dark matter, so we can't detect whatever dark matter is deflected by dark, not deflected, is scattered by other dark matter. We can't detect it, so it's dark. For us, it's dark because we don't have the right instruments, okay? And if we had the right instruments and were made of dark matter, maybe I could still not read off the dial because I have no dark matter in me. So if it really doesn't interact, it's a problem. But gravitationally, it has an effect. That's why we see certain things. So, I mean, this is dramatic because, well, the zero you can forget, because it says that 95% of the stuff, of the matter energy density that fills the universe, if Einstein's theory is correct, because all of this, all the interpretation of the raw data, this diagram, more complicated models, they all depend on Einstein's theory plus our theories of the standard model of particle physics put together in combination on curved spacetime. All of this relies on that, and if there's no mistakes have been made, the theory says that what we always believed is all the matter in the universe is only 5%. So you can, if you believe firmly in Einstein gravity, and you believe firmly in the standard model of particle physics put on curved spacetime being treated there right, and people who calculate the stuff having made no mistake, if you believe in all of that, which is quite reasonable to believe, conservative point of view, right? We have a major discovery here from recent observational data of the last 20-25 years. We discovered 25% of matter in the universe in the last 25 years, which before went undetected. This is why people are so excited about this. They say, if this is true, But it always comes with a caveat if the underlying theories that have been used to extract this splitting of numbers are correct. Einstein theory being one of them. And of course, you remember I said maybe you cannot make the symmetry assumption first and then calculate. Maybe you have to do this in another way. And there are people who claim you need to do that. So some people say maybe some amount of this, maybe not everything, but maybe the proportions shift a lot if you do the good old physics properly. So maybe Einstein theory being correct, quantum field theory being correct, and also people not having miscalculated who calculated the background theory for that, but maybe they made a mistake in line 1. Okay? And therefore it's very valuable what some people try, that they say don't make the symmetry ansatz too early. It could be that if you average later that this shifts, and maybe then this is 95% and this is 5. And you say, yeah, there is something, okay. Okay, and you have to work on it, and I mean, also the smallest Mercury precession can take you somewhere, 4 arcseconds per century, so we shouldn't discard this. But this major result would look different, okay? So always keep in mind what it's based on, and always question where else could this come from. But of course, it's excellent for research grants, I take it, so therefore you follow the standard route. So anyway, so you have this result in the universe.
Isn't there a theorem which allows you to insert symmetries before doing this?
That's different. What Julian is referring to is, and should have emphasized this more, if you have a field equation, and Einstein gravity is not an exception, then you should always insert symmetry assumptions on the objects about which the field equations talk, in this case on G. You should always insert it at the level of the equation. If you remember Giulini's talk, a symmetry is something that takes a solution to a solution. But this here comes from an action, namely S grav plus S matter, this total action by variation with respect to all possible fields that are in there. And you could say, oh, I could implement this already up here, and then I only need to vary, for instance, in cosmology, with respect to the scale factor, because that's the only degree of freedom that survives. This here is usually illegal. You must not insert a symmetry ansatz into the action and then derive. And it's pretty clear why. Think of actions in classical mechanics. There you say, you call this curve special, or a solution of your equations, if any neighboring curve, however slightly it deviates, if slightly deviating neighboring curves don't change the value of this guy to first order, right? That's the stationarity principle. But now assume I put in the symmetry ansatz from the beginning, then I can no longer compare to this curve. It's crucial that you say any neighboring curve that deviates only a little shouldn't change the value by more than a quadratic order. Not just one, but any. But now imagine you put in the symmetry ansatz first. In that case, for your curves, you would only compare to other curves that satisfy a certain symmetry condition. Then you're comparing to fewer competitors. If you compare to fewer competitors, you can be more easily better. So the point is, you can have fake solutions if you insert it here. Okay, that's the point. You can have fake solutions. So this is not allowed, but there's the principle, it's the principle of symmetric criticality, or stationarity, but traditionally it's called criticality. It's by Palais. And he gives conditions, under what conditions you can plug in the symmetry. And very roughly speaking, if your symmetry algebra, you know that the symmetry comes with an algebra for the metric, if the symmetry algebra is the algebra of a compact group, how do you find whether it's the symmetry algebra of a compact group? Well, you calculate the so-called killing metric. It's the same killing, but a different object. You calculate the so-called killing metric from the structure constants of the algebra. So you have the structure constants of the symmetry algebra. You remember? You square them. Up, down, down, up, down, down. You contract this one with that one and this one with that one, and then this A and B remain open. You call the result KAB. It's called the killing metric. And I think if it's negative definite, then the Lie group to that Lie algebra is compact. I think that's right. So you very quickly, I give you an algebra, for instance, our rotation algebra. You could check this guy is a negative definite 0,2 form. And then you know, so for a symmetry, I can do it because Palais says for compact groups, you can do it and then vary, and it's the same. But it's a very rough statement, and it's only sufficient, and application requires sufficient care, but roughly something like this. But that's right. But in general, that's what Julian, I think you meant. Yes, yes. Is you're not allowed to do that. But that has nothing to do with cosmology. Yes.
Isn't it possible that this dark matter are just ordinary particles but unseen by us, cold or just hidden somewhere?
Yes. So some people consider that. They say it could be the standard model over again, but with a little slash on each particle. And the slash has no interaction terms with the non-slash particles. Yeah, but that's dark matter. So nobody knows how to model that in detail.
No, but I mean something like astrophysical objects, like matter or something like this. Is it written out? Do we know it's not true?
There are many possibilities. It's not believed that it's of standard model type. But again, who knows? Okay, but it doesn't look like it. It simply doesn't look like it. Okay.
Is there a static solution on this graph?
A static solution? You mean where the universe does not expand?
Yes.
Well, you need to. You can check. You can require A of t is constant, and you know that rho goes like a to the minus n. You know that h goes like a square root of rho. You look at the densities and you look how they need to go, if that's possible at all, such that there is the solution is static. Yeah, you can check that. Yeah. Okay. So I think we need to postpone any questions to after the pizza event. Thank you.